All right, so today we're going to finish up section 2.2, okay, which is on using the calculator to find complete graphs. This is pretty short, so we'll probably be done this really quick, and then we'll look at section 2.3. All right, so let's start out with an example for our company. Okay, and this company has two types of costs. Okay, they have what's called fixed costs and variable costs. Okay, a fixed cost is a cost that's fixed. It doesn't change. It stays the same. A variable cost is a cost that changes depending on how much product you produce. Right? So maybe the fixed costs here are salaries. Right? Regardless of how many t-shirts this company prints, they pay the same salary to the employees. Okay, so in this case, it's $200,000. That's the fixed cost for this company. And it costs them $1.50 per shirt that they make. Now, after they make the shirts, they sell them for $4 each. Okay, what I want to do here is try to come up with two equations. One that models the costs, both the fixed and the variable, and then one that models the money that they take in, which is called revenue. Right, so we're going to find graphs on the calculator, but first we got to figure out what the equations are for cost and revenue. Okay, first thing we got to do is pick a variable for the number of shirts that are made or sold. What would be a good letter to pick for our variable?
S.
S?
For shirt.
Yeah, I think S for shirt, that would make sense. The only thing is sometimes my S kind of looks like a 5. So yeah, I'm going to use X. Just so my S doesn't look like a 5. Right, so we're going to find the cost as a function of X. And the revenue as a function of X. Right, Corey, you think you could give me my equation, this is just for the cost.
The cost for everything, so...
Yep, total costs, yep.
So 200,000, or sorry, 150x plus 200,000.
So yep, the plus 200,000, and what'd you say for the first part?
150x.
Yeah, 1.5x. Now you could have said it the other way around too, that's fine. If you were going to say 200,000 plus 1.5x, that's fine. Okay, so there's our costs. Graham, what about our revenue?
I don't know.
Okay, what is revenue? Do you know what revenue means?
No.
Revenue, that's the money they take in.
Okay.
So that's like their money they make.
So 2.5.
Okay, I know what you're thinking. You're thinking the profit after you subtract out the costs. But revenue in this example is just how much money they take in.
4x.
Yeah, 4x. Now, if we wanted profit, which I think, Graham, is that what you were kind of thinking?
Yeah.
Profit is when you take your cost, subtract your revenue. Or, I'm sorry, revenue, subtract your cost. But those are our two equations we're going to graph. Okay. Questions on those? All right, so let's graph them. Okay, so in y1, type in 1.5x plus 200,000. Okay, y2, type in 4x. And we're going to need a pretty big window. Okay, our y-intercept is up at 200,000. So let's go even higher. Let's go to like 500,000. Okay, X max, that's how many shirts we sell. So that's 12,000 shirts. I'd say let's even go a little higher. Let's go 100,000. Don't worry about negative shirts. Okay, don't worry about negative revenue here. That wouldn't make sense. Or negative costs. Cost is positive, revenue is positive. Okay, and then hit graph. Let's see what we got. Yeah, actually, that's pretty good. All right, so the line in blue, the way I did it, that represents your costs. The line in red, that's your revenue. Okay, and we'll talk more about that picture in a second. Any question on that? Okay, so for find a complete graph, I think all I would do here is, that's it, show the graphs.
That's pretty cool.
Yeah, it's pretty quick, huh?
Yeah.
I want to do that.
I do too.
What do we give it over?
Just throw it in the notebook right there.
That'd be
Say
awesome.
you work.
Is there
Yes.
what we do on the homework for finding complete graph?
For finding a complete graph, you would just do it on the calculator, and you could write on calculator.
Alright.
Yeah. All right. So the break-even point. Okay, we're still going to use that last example, so don't clear it yet. Okay, break-even point. That's where your cost and your revenue are the same.
I found it.
Okay, where would that happen on the graph we just drew? Yep.
Where they intersect.
Yeah, it's where the two lines intersect. So where the lines cross. Or intersect is even a better way to say it, because that ties in with how you find it on the calculator. Okay, so where the lines intersect, where they cross. So now what I want to do is find the number of shirts that the company has to sell to break even. Okay, we're going to do it two ways. One way algebraically, one way graphically. Since we just mentioned it's where the lines cross, let's do it graphically first. Okay, does everybody have the definition of break-even point and where it is? From there up. All right, so graphically. Well, we already have them graphed. Does anybody remember what you press on the calculator to find where two lines or curves cross? Buttons, Steph?
Second one, trace.
All right, good. Yep. Second, press trace, and the fifth option down is intersect. Perfect. Pick a point somewhere on the first curve you want to find, second curve. Does the guess really matter here?
No.
No. It's not like there's another intersection somewhere else. Okay, there's only one, so. All right, so it occurs at 80,000. All right. So in the homework, all you'd have to do is do second calc intersect. You'd write on calculator, and then write down the answer. 80,000 shirts. Hey, that's all there is to it graphically. Algebraically. What did we say? What's the definition of the break-even point? It's where...
So it equals you cross.
The two lines intersect.
Well, for now, let's not use graphs because we're going to do it with algebra. It's what?
Wouldn't it be the two equations are equal to each other?
Yeah, it's where the cost equals the revenue. Right? It's the point at which the cost and the revenue are the same, or where they're equal. So to do it algebraically, take your cost, set it equal to your revenue. Okay, your cost was 1.5x plus 200,000. And your revenue was, I think it was 4x. Okay, now as we solve this, we're going to get the 2.5x that Graham mentioned earlier. Okay, subtract 1.5x. And if you divide each side by 2.5, you get x equals 80,000 shirts. Okay, once they sell 80,000 shirts, it will have cost them $320,000 to make them, and they will have made $320,000 in revenue. So at that point, they've broken even. Anything beyond 80,000 shirts, now they're making profit. That's a lot of shirts. Okay, any question on solving that algebraically or graphically? Okay. So that's it for section 2.2. 2.3. So in 2.3, we're going to solve different kinds of equations. We'll look at linear equations. Under that, we'll look at absolute value as well. And then we'll finish up with quadratics. Okay, if we have time, I'm going to show you where the quadratic formula comes from. Okay, I'm sure a lot of you have it memorized, but I bet a lot of you haven't seen kind of where it comes from. All the A, B's, and C's. So we'll see how much time we have. All right, since we're going to solve equations, first thing I'll do is just define what an equation is. So an equation is basically equality between two expressions. Right, so you've got something on the left, something on the right, and an equal sign between them. Okay, if your equation uses a variable, and let's say we happen to use the letter x, we could say we have an equation in x. All that means is we have an equation where the variable is x. So if I said on the last problem, write an equation for the cost as a function of x, that basically means what I've written right here. Use x as the variable in your cost equation. Okay, to solve an equation basically means to find all the values that make it true. Okay, how many solutions does an equation have if you solve it? Yeah?
It's usually like one.
Okay, so if you have any, vote for one. Any other thoughts? Yeah?
Well, depending on how many like, exponents it has, depends on how many answers it can have.
Yeah, it really depends on the kind of equation. Okay, I could come up with an equation that has no solution, or I could come up with one that has infinitely many, or anything in between. Right, so it depends on what kind of equation you're going to solve. Generally, for a linear equation, one solution. Yep. Okay, and there's really a few different kinds of equations you can have. Okay, one type of equation is an identity. Okay, an identity is an equation that is always true. It's an equation that's always true. Okay, you can't make it false. Okay, there's an example of an identity. Okay, the reason this is an identity is watch what happens when you start to solve it. 3x plus 2 on the left. If you distribute, you're going to have 3x plus 3 minus 1. Plus 3 minus 1, that's plus 2. You'd end up with this. And then everything you could subtract 3x from each side, but then you're going to end up with that. 2 equals 2. Okay, whenever all your variables cancel out and you're left with a true statement, that's an identity. Meaning plug anything you want in for x, anything works. So that's an identity. Does anybody know the kind of equation that you can solve? It's not an identity, but there might be one number that works, like x plus 2 equals 5. It's not an identity because there's only one number that makes it work. Does anyone know what you call that? Okay, that's called a conditional equation. Okay, a conditional equation is true under the right condition. Okay, if you pick the right value for x. Okay, in this case, x equals 5. Okay, there's also one other kind of equation. I didn't put this one up here, but it's an equation that you can't solve, like this. This equation is impossible to solve. If you try to solve it, it's kind of like an identity when you subtract 2x from each side. all your letters disappear, but look what you're left with. 3 equals -4. That's not true. So that means no matter what you pick for x, you will never be able to make this true. Right? So there's 3 types of equations: identities, conditional equations, and ones that can't be solved. For this one? You could call it a contradiction. It's a contradiction. It's something that can't be solved. I mean, it is false, but I don't think they'd call it a false equation. Probably a contradiction is the closest thing I can think of. All right, so I'm sure you guys already know this, but if you want to check if an answer is a solution, you fill it back in, and see if you get a true equation. Right, so what I want to do here is check that -2 is a solution. All right, Madison, to check if -2 is a solution, where do I fill it in? Yeah, I'm going to fill it in everywhere I have an x. So we get -2 cubed. Just be careful here, minus -2 plus 6. And we're hoping it comes out to 0. If it does, we're good. If it comes out to something other than 0, like if it comes out to 2 equals 0, that's false. So it means our answer doesn't work. Tom, what's -2 cubed? Yeah, -8. Okay, and then Heaven, what's minus -2? Good, it becomes +2. 6 equals 0. And I think now we can see -8 plus 2. It's -6. -6 plus 6, does that give me 0? So -2 is a solution to that equation. Okay. Anybody remember how many times I said a cubic equation can turn? Yeah?
Up to 2.
Up to 2 times, which means it could have how many solutions?
3.
Could have 3. So maybe this problem looks something like this. One answer at -2, another one there, another one there. Okay. Or maybe it looks something like this. I know it goes through -2. Maybe it doesn't turn enough to come back. Or there's a third case where it comes up, comes down, and just touches the axis and goes back up. All right, so it could have 1, 2, or 3 solutions, this problem. You think a cubic could have no x-intercepts? Is that possible, to have no x-intercepts in this graph? Brad, what do you think? Why not?
Because it goes in front and down and everything off in one direction.
Yeah, basically this graph is going to go down in one direction forever. It's going to go up in another direction forever. And it's always connected. So if you're going from -infinity to +infinity and you're connected, well, you've got to go through 0 somewhere. You have to. You can't skip over it. It's kind of like the idea if you had water at 40 degrees and you're going to get it to boiling at 212. Well, it's like asking the question, is it going to be 105 degrees at one point as it starts to boil? Yeah. If it's at 40 and it's going to go to 200-something degrees, it's got to go through every single temperature up to boiling. It can't skip a temperature as it's being heated. Same idea. All right, so this is basically the simplest form of a linear equation. Ax plus b equals 0. A and b can be any real number you want, except a can't be 0. If a is 0, what happens is this. You end up with just a number on the left-hand side. Okay, that would kind of be like graphing the equation y equals 2. That's not a linear function. It's a constant function. Okay, but to be according to our book, to be a linear equation or linear function, it's got to have a slope for x. Right, so this one doesn't quite look as simple as that one, but really this is just a linear equation. We could rewrite this one just like that. Right, so we'll just go through it real quick. Hopefully Algebra 1, everyone can do that, no problem. But that's why we'll go through it. DJ, what's the first thing I got to do here?
You gotta distribute.
Yeah, and can you do my distributive wherever you have to do it? Tell me what you get.
Okay, I got 6x minus 6. Right, for the first one there.
Yeah, can you do that first one more time?
Sorry, 4x minus 6.
Yep.
Plus 3x plus 13.
Good. All right, so we get our distributive property. We had to do it twice here. Next thing, combine like terms. Olivia, can you combine my like terms on the left-hand side for me?
7x minus 3.
Good. 7x minus 3. Okay, now we have to put all the x's on one side. Shelby, what would be easier to do here? Put everything on the left for the x's, or put the x's on the right?
Probably put the x's on the left.
Yeah, I would put the x's on the left and we can avoid negatives. How would you put the 5x on the left?
2x, and then if you move the negative,
Oh yeah, we can do both. Sure.
then it'd be plus 5 on the other side.
Yeah. So she did minus 5x to get that 5x on the left. She did plus 3 to get all the numbers without x's on the right. Step, divide by 2. X is 5/2. Questions on that? So notice at this step right here, okay, we could make it look just like this if we wanted. Ax plus b equals 0 by writing it like this. 2x minus 5 equals 0. Does everyone see how I made what's on the left look like what's on the right? Now this is what you could type in if you wanted to graph it. Type it in as y equals 2x minus 5. Look for where it crosses the x-axis. It'll be right there, 2.5. All right, absolute value. Does anybody know what shape an absolute value is if you graph it? Yep.
Is it like a V?
Yep, exactly. It's a V shape. Good job. Okay, the reason it's a V shape, let me show you. Okay, if I were to just graph the equation y equals x, okay, what it would want to do is look like a line with a slope of 1 going through quadrants 1 and 3, just like that. Well, with the absolute value, this part, we have a problem. That part can't go negative, so what it does is it takes and basically flips it up, so that way it's positive. Okay, so the part that would want to be going right here for the line y equals x, it's basically reflected over the x-axis and brought up top. Right, so you get a V shape. How many times could that V shape cross the x-axis? Cross or touch it? Yep, once, just like in the picture here. What else? Yep. I could break it twice if I brought it down. Like if I just put a minus 2 on the end. Now it'll cross twice. What's the other case? Yep.
Not at all.
None at all. Okay, if I shifted it up, it wouldn't cross at all. So that basically tells you how many solutions an absolute value equation can have. 0, 1, or 2. Okay, we're not going to spend a lot of time solving it on a calculator. We'll just do it with algebra. Okay, so the idea is we're going to take the original problem. We're going to make sure that the absolute value expression is by itself. And then after that, we're going to split it into two equations. Okay, your first equation is going to be exactly the same as the original problem. Just take away the absolute value bars. Okay, literally, just copy the original problem over and erase the absolute values. Okay, that'll be your first equation you solve. Okay, and then your second one, you're going to take the original problem, you're going to copy it down again. You're going to take away the absolute value bars, but you're going to do one other thing. Change the sign of the number that's by itself on the other side. Okay, that's what negate means. Change the sign of. So the very first step I underlined, make sure we isolate the absolute value expression. You don't have to do that in this problem. It's already done. Okay, but let me show you a problem that's equivalent to this, where you'd have to do it. In this problem, the absolute value is not by itself. There's something else on the outside. So the first thing you'd have to do is plus 1. Plus 1. Now you get the absolute value by itself. Okay, what if I had something like this? Yeah, you divide each side by 2, and then the absolute value would be by itself. Any question on what I mean by that now? Isolate the absolute value? Okay, you can have stuff inside, nothing on the outside on the same side. All right. Now let's split that up. Okay, first equation, same as the original, just take away the absolute value bars. Okay. Anyone think they can tell me my first equation? Yep. Equals 5. Okay, so copy down the same one as the original. Just take away the bars. And how about my second equation? Graham?
2x plus 3 equals -1.
Perfect. Okay, so 2x plus 3 equals 5. And 2x plus 3 equals -5. Right, now we solve it. So in this case, we're going to get x equals 1. Okay, minus 3 and divide by 2. Okay, and make sure you put and because these are both solutions. What would my other solution be? -4. Right, so minus 3, you get -8, divide by 2, -4. Right, so this tells us it's a V shape. If you graph it, it would cross the x-axis at -4, +1. Okay, any question on absolute value?
Can you grab that one?
Can we graph it? Yep. So to graph it, what I need to do basically is write it so the -5 is on the other side. Okay, get it equal to 0. So absolute value of, was it 2x, what was it?
2x plus 3.
2x plus 3. Okay. Minus the 5. And now we're going to look for where it equals 0, because that's what it would equal now. So just do zoom 6. Okay, notice it crosses the x-axis at -4, +1.
Wow.
Okay, question? It's a nice way to double check your answer if you want. All right. Last type of linear thing we're going to look at before we get into quadratics is a mixture problem. Okay, you've probably seen these before. Okay, basically, to solve a mixture problem, we have to set up two equations. Now, this is kind of Well, here you can actually do something that's a little quicker. Okay, if we do something in our head, we can do it with one equation. Okay, I'll show you what both equations would be, but then I can show you how to do it with just one of them. Okay, so when we mix two things together, okay, the kind of problem they're going to give you is they'll say, well, you're going to mix a 10% solution and a 20% solution. I want you to mix them together so that when you're done, you have a 13% solution. And I want you to have 50 gallons of it. Okay, that's the kind of problem they're going to give you. So one equation that you could set up would be one for the total amount. Okay, I'm going to take X amount of the first solution, Y amount of the second, and I want a total of, whatever, 50 gallons. Okay, the other equation you set up has to take into account the concentrations. Okay, and this is the one that's more important, especially if we're going to try to do something in our head. So the second equation says take the concentration of the first thing you're mixing times how much, plus the concentration of the second thing you're mixing times how much, and that's equal to the final concentration. Maybe I should put that in. So that's the final concentration times the total amount that they want you to have. As I said, there's a shortcut where if you were going to solve these as two separate equations, it would be like a system. You'd have two equations, two variables, and you could use substitution. But we're going to try to do the substitution in our head, so that way we can get away with one equation. Right? And the substitution that we need to do here, we've already kind of done it before. When we did the interest problems, and if you invest X amount at whatever, 5%, you have 10,000 minus X for the rest. Okay, that's as hard as the substitution is going to be. All right, so the two solutions we're going to mix, one of them is 10%, one of them is 25%. Okay, we'll mix those together. And I want to end up with 15 liters when I'm done. And I want it to be a 12% solution. Okay, so how much of each solution do we need? Before we even set up an equation, what do you think first thing we should do is? Yeah?
We do multiply 15 and make this by 12%.
That's actually going to be part of the equation, and we're going to do that out. So yes, we are going to do that. But I wouldn't do that right away. What do I need before I can set up my equation? Graham?
Amounts of A and B.
Yeah, I need to pick some amounts for A and B. I need some variables. So now we can do it two ways. We can either say we're going to pick two variables and then do substitution. Or I think we can do it with just one variable. So Graham, how much of solution A do we want to use, or how do we represent it?
Maybe
How can we represent how much of solution A we're going to mix?
how many liters you put in.
Yeah, how do you want to represent it? Because we don't know it right now.
Do I just like say right the number? It does that.
No, we can't pick a number for it. We're going to solve for the number. But how do we represent something we don't know?
X.
Yeah, you could pick X.
Can we triangle?
You could do triangle. You could do A for solution A. Okay, I'll use X because that's what Graham said.
Y.
Now we could do it as Y, or how else could we do it? If we know we're going to use X, and we want a total of 15, Brad?
15 on the second.
Yeah. So there's a shortcut to eliminate using a second variable. Now we can jump right to the second equation. concentration times amount. I should mention here as a decimal. Okay, always a decimal. Okay, what's the concentration of solution A as a decimal? Tom?
0.01.
That'd be 1%. 0.1.
Sorry.
0.1, yeah. Or you could put 0.10 if that's what you meant. But so concentration times, Heaven, how much of solution A are we going to use?
10%.
Yep, and how much of that solution? How did we represent it? Yeah, X. So concentration times amount plus the concentration of the other solution, 0.25. Okay, and DJ, how much of that one?
15 minus 6.
Good. Equals, and now this is the part that Corey mentioned, we're going to be able to do out. Our final concentration is 0.12 times the final amount is 15. And so we got 0.10x. Okay, make sure you do a distributive property there. So 3.75 minus 0.25x. And then 0.12 times 15. Let me just double check that. 0.12. No, okay, 1.8. So let's combine like terms and move the 3.75 to the other side. What's 0.1x take away 0.25x? Negative what? Yeah. Okay, that's going to be 1.8 minus 3.75. Is that, let's see, negative 1.95, I think. Bless you. Okay. Last step, divide each side by negative 0.15. Right, so x is 13. And what did x represent? Which one? Bless you.
Solution A.
That was solution A. So solution A, 13 liters. How much for solution B? 2. So if you mix them together, you'll get exactly 15 liters, and it'll be at 12% strength. Okay. Any question on that? All right, so last thing we're going to look at is quadratics. So a quadratic equation has this form: ax squared plus bx plus c. And a, b, and c can be any real number that you want, except a can't be 0. Why not? What would happen here if you let a be 0? Graham?
That'd become linear.
Yeah, it would become this. It would become linear. All right. So if we want to have a quadratic, you can't let a be 0. Okay. One way to solve a quadratic equation is to factor. Okay. Factoring works great if you have the right numbers. It can be kind of a pain, especially in Algebra 1, if it says factor this problem if possible. Then you don't even know if you can factor it. Right, but I will tell you this one is factorable. Okay, you don't have to do it here, but when you're going to factor something, what do you always want to make sure of before you even start? It's already done here. Maybe a couple things. Yeah, Andrew?
Won't set it to 0.
Yeah, you want to make sure it's set equal to 0. Anything else? How about on this other side? Yep. Yeah, if you can factor out or divide through by something, you can maybe reduce it. You want to make sure it's in descending order. X squared, then the x, then the constant. And generally, we like the number in front of x squared to be what? Positive. All right. If you factor with a negative in front here, it's going to mess up all your rules for factoring. All right. So first thing we want to do is put 2 sets of parentheses. And what could I multiply together here that would give me my first term? What times what is 2x squared? And there's only one thing we can do. Yeah, 2x and 1x. Good. We've got a positive middle and a negative constant. What does that mean about my signs?
Plus, the other's gonna be negative.
Yeah, one's plus, one's minus. Does it make a difference where they go?
Yes.
Yeah. So I just guessed. If it doesn't work, we can always switch them. And now I need 2 numbers that multiply to give me 3. 3 and 1. Does it make a difference where we put them? Yeah. So I'm just going to do 3 and 1. Okay. Did we factor it correctly? You think, Olivia? All right, let's check it. What's 2x times x?
2x squared.
That's good. 2x times 3.
6x.
And what's x times negative 1? Negative 1x is 6x, take away 1x, 5x?
Yes.
Yeah. And then negative 1 times positive 3 is negative 3. So we're good. We factored it correctly. Some things that could happen when you're factoring is you might have to switch your numbers. You might have to switch your signs. All right. Now, just looking at what this says. Something times something equals 0. How can that happen? How can something times something equal 0? And this is the reason why you always set it equal to 0. You can't do this with any other number.
You want the 2 has to be equal to 0 itself.
Right. If you know you multiply 2 things together and get 0, one of them or the other one is equal to 0. Or both. Yeah, one or the other or both. So let's set that up. Either 2x minus 1 equals 0, or the other factor equals 0. Okay, solving the first one, we get x equals a half. Second one, x equals negative 3. Okay, so when you can factor a problem, very quick to solve it, usually. Okay, any question on the factoring? All right. So if you can't factor it, we can use the quadratic formula. Where the quadratic formula comes from, it's pretty easy to do it. I don't know if I want to go through the whole thing in a lot of detail, because it does take like 5 minutes to do it. And there's really a word problem I want to get to at the end. But for this part, just kind of watch me do a little bit of it. Don't write. You don't have to write this down. And I just want you to start to see where some of these letters come from. Well, the way you get the quadratic formula is you take your quadratic, you set it equal to 0, and you complete the square. Okay, first thing you want to do when you complete the square is put the constant on the other side. Next thing you have to do when you complete the square is you have to have a coefficient of 1. So to do that, I could divide everything by a. Okay, it gets a little messy. Now I just have x squared. X squared. The coefficient is b over a. Then you leave a little room, because now you're going to complete the square. And to complete the square, remember you take half of something and square it. So what you'd have to add to both sides is this, but take half of it. So you put a 2 in the bottom, that cuts it in half, and square it. So it's really b squared over 4a squared. And you'd have to add the same thing on the other side. B squared over 4a squared. Okay, and I think I'll do one more step and then maybe start to see where some of the quadratic formula comes from. Okay, this is going to factor very nicely. It's going to factor as x plus b over 2a. Okay, that's just when you complete the square, you're making it so it factors as something times itself. Okay, and on the other side, what I would need to do is come up with a common denominator. Okay, common denominator is going to be 4a squared. Watch what happens to this fraction on the left if you make a common denominator. So, multiply by 4a, and then multiply by 4a. Anybody see something there now? Minus 4ac. Okay. That's where the quadratic formula is starting to come from. And b squared minus 4ac. Right, so we're starting to see some of it. So you have b squared minus 4ac all over 4a squared. I'll do one more step, then I'm going to stop. Okay, you take the square root of each side. Watch what happens here. You get x plus b over 2a equals the square root of b squared minus 4ac. What's the square root of 4? 2. What's the square root of a? A. So there's your square root of b squared minus 4ac all over 2a. Okay, and I could finish the last part by bringing the negative b, bring the positive b to the other side as a negative. Okay, but I'm just trying to show you it's actually not that hard where it comes from.
Yeah.
I mean, it's not something that would take hours and hours. You can do it in like 2 minutes, 3 minutes.
It's the variables. I'm not sure.
Yeah, it's all letters, so if you get confused with the letters, that can be hard. Yeah. But it's the kind of thing I can do without in under 3 minutes if I just have to do it. Yeah. Does everyone understand kind of the basic idea, though?
Yeah.
You're just completing the square, except it's all variables. That's what makes it a little hard. Okay, don't worry about having to show me that. Okay, you're just going to have to use this on a test. Negative b plus or minus square root of b squared minus 4ac over 2a. This part under the square root is the discriminant. We've talked about that a little bit. Okay, just like when you're going to factor, okay, to use this formula, make sure you put it in standard form. So let's try this one. Okay, we'll do this one and then we'll start to look at a word problem, and if we don't finish it, that's okay, but the next one will be our last problem. Okay, what's my first step? Here, this isn't quite ready yet to plug in. Yeah, set it equal to 0. 2x squared plus 2x. Bring the 1 to the other side. Okay, next, let's just identify A, B, and C. Okay, what's A here? Okay, Corey? I'll let you do B.
Okay.
What's A?
2.
Good. Andrew, what's B?
2.
And C? -1. Okay, let's fill in it's a quadratic formula, see what we get. So negative b. Okay, plus or minus square root of b squared minus 4ac all over 2a. Okay, now Now we just have to do out the arithmetic, see what we get. Okay, we have -4 and -1. Shelby, what's going to happen with those two minuses?
They're gonna make it a positive.
Yep, become a positive. 4 times 2 is 8, plus 4 is 12. Okay, square root of 12, how can we reduce that? Yeah.
It can be reduced to 2 square roots of 3.
Good. 2 square roots of 3. And what can you divide each one of those numbers by? Yeah, they're all divisible by 2. Okay, so the final answer is -1 plus or minus square root 3 over 2. Okay, usually we only use quadratic formula when we can't factor it, because we're going to get a messy answer. Okay, any questions on the quadratic formula? Okay, for now, don't worry about negatives under the square root or imaginaries. We'll get to that later on. We're going to skip that one. All right, so this will be our last one. I think the hardest thing with this one is visualizing what they really are looking for, and then setting up an equation. Okay, if we can set up the equation, I'm fine with just using the calculator. Okay, if we can do it that way. It says, basically, you've got a rectangular piece of paper, and you're going to cut squares out of each corner so you can fold the sides up and kind of make like a tray. Right? So something kind of like that. You've got a rectangular piece of paper. You're going to cut the corners out so then you can fold on the dotted lines. Okay, and what I'm telling you is the squares that you cut out of each corner are 5 by 5. Right, so that's the square that we cut out of each corner. What we don't know is the length and width of the original piece of paper. But what I will tell you is when you fold this up, okay, the volume that would fit inside it is 2,040 cubic inches. Okay, find the dimensions of the original piece of cardboard if you were to lay it out flat. Okay, before we cut the corners off. Okay, first of all, does everyone see what they're asking for? You can visualize folding on those dotted lines, making like a little tray, kind of. All right, well, first thing is we're going to be finding volume. Okay, so what is the volume of, almost think of this book as like the tray. This is a prism. Okay, what's the volume of a prism? Rectangular prism. Yeah? Good. So we're going to need that. Length, width, height. Now, what is the original length? There's a sentence in here that says something important about the length. Yeah?
And the length is twice the width.
Right, that's important. So now we can represent everything basically in terms of W. Okay, but let's just write that off to the side. Length equals twice the width. Okay, if you want, change what I circled to 2W. The length is twice the width. There's my length. Here's my width. Here's my height. So now all I really need to do is figure out what's the width, what's the height. Yeah, the height's going to be 5. Okay, that's the edge, and if you fold that up, it would have a height of 5. Okay, so we've got that. Okay, volume. Do we know the volume?
Yeah.
Yeah, the volume is 2,040, so we know that. Now we just need the width. This is where we'll have a variable. Okay, how would you represent the width here? Just think about it. Think about it for a second. Just let people look at it. Right, so this is what we're trying to represent right here. This is the width of my box once I fold it up. Not the original width of the piece of paper. I think that could have been confusing. So on a test, I'd make sure that's clear. What's this part in red?
Would
Yeah.
it be like 10 minus W?
Close. Very close. Yeah.
W minus 10.
Yeah, W, take away 5, take away 5. So W minus 10. So I've got W minus 10 is my width, and then I have to double my width, 2W minus 20. Right, if we do this out, we're going to get 2W squared minus 20W minus another 20W is minus how much? I think I heard someone say it. Yeah.
40W.
Good. Minus 40W. And then 20. Negative 20 times negative 10 is plus 200. Okay, rather than distribute that 5 out, what could I do on each side? Yeah, I could just divide by 5. It's going to make the numbers a little smaller. So it's 408 equals 2W squared minus 40W plus 200. In fact, anybody see one more number I could divide by?
2.
Yep, divide everything by 2. 204 equals W squared minus 20W plus 100. And I would bring that 204 to the other side. So it's going to be minus 104. And there's basically your equation to solve. Okay, we could just graph it. Okay, see what we get? Let's type it in real quick rather than factor it or use quadratic formula. Right, what I'm going to do is just try to zoom out a little bit. You can see part of the parabola. And now I can see the other part. Negative width. Okay, that wouldn't make sense. So I'm going to do second calc 0. And I'm going to find the one that's further to the right. Okay, it's somewhere. Once I see it, now I can start to see it. Pick a point left, pick a point right, take a guess, and it says the width is about 24.28. And if you know the width is twice, the length is twice the width, just take 24.28 and double it. So it should be about 48.56. Right, so that's definitely a little tricky key to go through, but we'll try another one tomorrow. And again, if you get stuck on the word problem, don't worry. This is not a extremely critical part for today. All right, so the homework, the first part is on a complete graph, 35 to 39 on page 88. Okay, most of that's just graphing. Just do it on the calculator. And then on page 96, 1 to 4, 9, 11, and 13. 16, 19, 24 to 26. 36 to 38, 52 to 54, and 58. So we'll look at that tomorrow, and then I think tomorrow we're just going to focus on one section. Okay, section 3, 2, 4. Sorry, section 2, 4 tomorrow.